What's up, everyone? Welcome back to Java with Hawa. So, I don't know why Loom always does this nonsense. like, it only works on one screen, which is really inconvenient, actually. Let me see. I don't know. It's kind of annoying, I'm not gonna lie. About like this. Um, where's Intel? My desktop is literally a mess. Oh my god. I'm so unorganized. Look at this video, it's already a mess. Okay, guys. So, okay, let me start over. All right, what's up, everyone? This is Hawa, Java with Hawa. You know what's going on. Okay, I got bored, so I'm making a video on intro to graphs today because I need to practice. I'm so rusty. I'm supposed to be studying my probability class right now, but I really don't want to do that. So let's do this instead. So I'm just gonna be showing here intro to graphs, directed, um, undirected, just how to implement depth first search and breadth first search and what they actually are. Sponsored. This is so good. I should try. Okay, so I'm just gonna start off with the graph representation that I'm gonna be using, and we're gonna have A. So if you don't know graphs already, they consist of things called nodes, which are these small things with some value or some information in them. So we have A. I drew the graph on my iPad, so I keep looking over there. A, B. Okay, so we're gonna start with the directed graph. Actually, we're only gonna worry about directed graph for this video. So I haven't made a video in so long. I've been so busy with school. A, B. Here is gonna be a neighbor to C or edge. C has an edge to E, and then B edge to D, and D edge to F. Okay, so wait, bismillah. Okay, so basically, what was I gonna say? Okay, so this is a directed graph. Directed graph just means you can only travel from the nodes in their respective directions. So as you can see, A and C here, the edge, so this is edge. Edges are what connect these nodes inside of our graph, and the nodes can also be called vertices. So here we can travel from A to C because we have a node A, and there's an edge going out from A pointing towards the node C, and that tells you can only go in that direction. So you can go from A to C, but in the directed graph, you can't go from C to A if there's no direction there, right? So maybe somehow there was another direction that goes from C to A, then you could say that's valid, but we're not considering that right now. So that's it. That's literally a graph. Here you can go from A, you can get to B, you can get to D, and then you can get to F, or you can go to A, C, E. So the most important thing dealing with graphs is obviously the traversal and how are we going to actually get through these nodes, get information about the nodes, find shortest path between them, find if some node exists in our graph or not. And the way we do that is through two types of traversal. So we can either do a depth first search. I'm going to abbreviate as DFS. It's so funny. Even after 2 years, I still can't write on this whiteboard. How embarrassing. Or we can do a breadth. I'm getting better though, low key. Breadth first search, which we can abbreviate as BFS. Also, I would do this on my iPad, but why am I not doing it? Oh, the audio always cuts out and it's just not reliable. So yeah, so we'll start with depth first search. So depth first search just means as you're traversing through the graph, you're going depth first. So you're going kind of much further in one direction and only exploring another direction when that direction ceases to exist. So for here, you're gonna go all the way down. If you start from A, you're gonna go to the child of A, which is B. Then you're gonna go to D, and then you're here. There's nowhere else to go, so you go back to A and maybe explore another neighbor that it had. So you go to C, you'll explore that all the way down, and then whatever happens, happens. So that's kind of the idea of depth first search. So you explore all the children first before going to the neighbors. But breadth first search is the opposite, and it's more of a lateral search. So you explore all the neighbors first of a specific node before trying to explore, I guess, deeper into its children. So, like for example, A. If we start with node A here, if we're doing a breadth first search, we would um, explore neighbor B, explore the neighbor C, and then once we have A, C, and B explored, then we can maybe go to B or C, whatever we choose, and explore its neighbor. So we'll explore D here, and then E from C, and then D to F. So we can see that now, like to try to implement it. Actually, let's see what would be the depth first search of this graph here. So if we start at A, we can explore B or C, our choice, but I'll go with B, and then we'll go depth. So we'll go to D, and then we're gonna go to F, and then C, and then E. I think. I hope that's right. Let me see. A B D F C E. That's looking good. Or you could have gone to C first, as I said, which would be A C E, and then B D F. So either way works. Now to do a breadth first, we're gonna explore laterally and like the neighbors. So we can choose again B or C, but we're gonna start with A, and I'll just say let's go with B first, and then C, and then maybe the neighbors of B. So like D, and then is it E? Yeah, E and F. E F. So here in the breadth first, we go A, B, we explore the neighbors of A first. So we kind of explore all directions more evenly. A, C, A, B. And then I guess we can from here choose whatever. But let's just say we did A, B, and then we explored C, and then we're gonna explore the neighbors of B. So D, we're gonna explore the neighbors of C, E, and then we're gonna explore the neighbor of D here, which is gonna be F. And that's all the idea is. And we're gonna implement DFS using a stack, and then BFS using a queue. So I'm not gonna like really explain. I guess I can kind of explain the code, but I don't want to write it out because the whiteboard is a bit slow. So anyway, here on the side I have this IntelliJ pulled up, and by the way, I've been using the struct course to practice. Super helpful. But like before I watch the videos, I kind of like to try it myself and try to explain it. So that's what I'm doing right now. Yeah, so I've just started with initializing the graph that we're going to use, and graphs can be implemented as adjacency lists or like matrices or like a collection of lists, collection of edges. But I think the most practical solution is adjacency lists, just because it's O of one, constant time to like look up our nodes, and then like we can just traverse through its edges much simpler. Much simpler? Is that a word? Much more simple? I don't know. I don't know. Anyways, so here I've initialized this graph I've implemented it as a hash map in Java with character as the key and hash set of characters as the edges because I don't want any duplicate edges. And then I also actually had a node class, which is really simple, but I was like, let me just use a character for now just to keep it simple. So as you can see here, this is the exact graph that is on the left. So I put in A, and its corresponding edges are B and C. So here C is an edge and B is an edge. And then I put in B, corresponding edge is D. And then for C, its corresponding edge is E. And then for, what's the last one? Okay, E has no edges, so that's empty hash set. And F is also an empty hash set, so it has no edges. So now that this graph is created and like we've populated the graph with all of our nodes and edges, we can actually try to start writing our algorithm. So we're going to start with the breadth first search iterative implementation, and then we'll do did I say breadth first? We're going to start with depth first, and then breadth first implementation. So public static. So here I'll just return a list of characters which will represent the characters, the ordering of the characters, just like how I wrote them here. And they might be a little different depending on which node get explored first. But anyway, so we'll return a list of type character, and I'll call this depth first search, and we're just gonna pass in our graph. So that's gonna be the way I implemented it, which is gonna be a hash map with type key, which is character, and type value. Maybe I should zoom in. I remember this was really tiny before in the past. Too much. Okay, and then the value is going to be a hash set, and in the hash set, we know that the type is type character as well, because we have this set of characters that represent the edges of a respective node. So we'll call this graph, and then we're also going to pass in a starting node, because if we're just given a graph, we obviously want to start somewhere, right? Like you can pick any node to start at, maybe E, maybe B, whatever you want to start. We can start from there. So we'll just start from A for simple case. So I'll just make that a character char, and I'll say start node, and cool. So for a depth first search, we want to use a stack, because the way the stack works is it's gonna go as deep as possible because of the way we pop things off the stack. So I can illustrate it here actually. So if we were to use a stack here to achieve depth first search, so this is going to be the stack, and let's say we start at node A, and let's just say we're keeping our running list of characters in our result over here. So we'll have A on the stack, right? And every time, the idea is every time we pop up the stack, since stack is last in, first out, every time we pop something off the stack, we're going to add its neighbors onto the stack. And so you can imagine that, let's say we start with A and we pop A off the stack. So this is going to be the first thing we pop, and then we're going to add it into our list for our result. Then when we pop A off the stack, let's add its neighbors onto the stack. So let's just say we add it in the order of C and then B. So now you can see that once we pop B off the stack, which is the last thing that's been added, so let's pop that off the stack, and we add it to our result list. We're not going to immediately add C. We're going to add the neighbors of B first. So that's going to be D, right? So instead of popping C off, we'll have added the neighbors of B, and now those will be at the top of the stack, and those will come out first. So D will come out, and then we'll also add the neighbor of D, so that'll be F, and then we'll put F. That will come out, and since there are no neighbors of F, we don't add anything onto the stack. And now we are at C, we can pop off C, add it to our list, and add its neighbors onto the stack. So we'll have E all the way up here, and then E would be the last thing on the stack. So we'll add E, and then we'll know that we can stop traversing. And similarly, for a breadth first search, we're going to use a queue data structure because queue is first in, first out. So we want kind of the way we add the neighbors in the breadthwise manner to come out just as we added it. So if we were to add A and then remove it into our list, and then we add its neighbors, and we know a queue is first in, first out, B would come out, we'd add its neighbors to the back of the queue, so it'd have D, and then C would come out. So it's going to continue in this manner, and it's going to come out in the correct ordering, and that's kind of how we're going to implement breadth first search. So that was just like a really fast, quick overview. I don't want this video to be like 30 minutes, so I'm going to try to code really, really, really quickly. This is just too small of a screen. Let me see if I can kind of make it bigger. Okay, whatever. So I'm going to start by initializing the stack that we're going to use for this algorithm. So we'll say stack, it's going to be of type character, and I'll call it the DFS stack equal to new stack. Okay, and then I'm going to make also the list of characters that I want to return that will contain like the ordering that I traverse this graph. So list character, I'll say node list equals new list, and I'm going to actually implement that as an array list. I don't know if the word is implement or instantiate. I don't remember. Because like this would be the ADT, right? Abstract data type. It's whatever. That's not important. Okay, so I think that's all we need to start. So the first thing we're gonna do is add the start node onto the stack, because that's how we're gonna actually begin a loop that keeps traversing through the neighbors and the other nodes. So if we start with an empty stack, then what are we going to return, and how do we know where to start traversing? So we'll say dfs stack.push, and we'll just push the start node on there. And then now we can traverse that. So while we're going to say, oops. So basically, while we still have elements on the stack, then keep popping the element off and adding its neighbors and repeat until the stack is empty. So we're going to say, well, the DFS stack is not empty, then basically let's pop off the node that's on the stack and let's store it into a variable. So I'll say char current equals DFS stack dot pop. Cool. And then we obviously want access to its neighbors, right? And since we implemented this as an adjacency list, we can get the corresponding value for the key or the node that we're on. We can set that somewhere and we can iterate through it to add its neighbors onto the stack. So I'll say hash set, and I think it's hash set of type character. I'm gonna call it the edges, and I'll say equals new hash set, and sorry, not new hash set. So we're gonna say equals the, like I said, the corresponding value. So we'll say our graph dot get the value that corresponds to this key or this node A. So I'll say graph dot get, and we'll say current. So get all the edges that are linked to the node A. So once we have that, we're gonna need to iterate through the hash set. I don't think we can just do a basic for loop because there's no like indices. So we're gonna use the iterator. So we're gonna say iterator type character, and we're gonna call it iter, and we're just gonna iterate through this edges hash set. So edges.iterator. So now we can have a while loop in here that says, okay, while iter.has next, so while there are still values in our hash set or more edges in our hash set, then put those edges onto our stack or those neighbors onto our stack so we can keep going in this depth first manner and still keep and still stay in this while loop so that we can get the right ordering or complete the traversal basically. So while iter.has next, then wait, what did I just say that we were gonna do? Oh, we're putting these values on the stack. So dfs stack.push iter.next. You could store these as an array list, honestly, to make it easier to iterate through, like using a for loop, but I don't know. It's up to you guys and like their specification. So dfs stack.push iter.next. I think that's it. Yeah, so this is gonna push all the edges that are in that hash set. And once that's done, I want to add this current value that we had popped off the stack into the resultant list, which is going to be the node list. So I'll just say node list dot add current, and yeah, so we have that going. We remove this off the stack. So this while loop is going to keep going, and at the end, we just want to return that node list that we created. And this should be good. So let's just run this and see what we get. So I'll say system.out.println depth. So we're going to call depth first search. We're going to pass in our graph, and our starting node is going to be A. And let's run this and see what we get. Run. Is it running? Okay. So A, C, E, B, D, F. So in this case, it's the same kind of thing, but instead of going with B first, we went with C first. But let me reorder these maybe. I wonder if sets actually have ordering. I don't remember. I think they do. I think Pythons don't, but I think Java does. Let's see if I do it this way. What happens? A, C, E, B, D, F. Actually, I don't think that made a difference. Whatever. A, B, D, F, C, E. Wait, is this right? A, B, D, F, C, E. Yeah, so A, C, E, B, D, F. That works too, but I don't know. Whatever, who cares? It still works. I wanted the other ordering. Maybe. That's weird that even when I did switch these, there was no difference. That's really interesting. Anyways, oh my god, 19 minutes. Okay, I need to implement breadth first search in 10 seconds. So I'm just going to copy. It's going to be the same thing as the breadth first search implementation. I literally said the same thing. It's going to be the same thing as the DFS depth first search, except, like I said, we're going to use a queue instead of the stack. Breadth first search, we'll call it, and I will say Q. We'll implement that as a new linked list. It's going to be called DFSQ. Oh no, okay. DFSQ dot add. Well, the DFSQ is not empty. DFSQ dot remove. So I guess the operation names in Java are different between the stack and queue. So don't forget that. DFSQ dot add. And this should give us the same exact thing, but in a breadth first manner. So let's call here breadth first search. Okay, and let's run this and see what's gonna be the output and if it's gonna be correct or not. A, B, C, D, E, F. That look right? Let's see. That looks right to me. A, B, C. Explore the neighbors. D, E, F. Oh my god! Yay! That's it for the graph.